Hello. In today's lecture, we are going to familiarize with Leibniz rule from advanced calculus under the section which deals with power series representation of analytic functions. So to make it into a better frame of words, we can say that in this section we are going to deal with the idea that every analytic function, that is a continuously differentiable function, will have a power series representation. So first of all, let's move to preposition 2.1, which is Leibniz rule from advanced calculus. The statement says let phi be a function from closed interval AB cross closed interval CD to the set of complex numbers be a continuous function and define another function g from closed interval CD to C by g of t is equal to integral from a to b phi of st ds. Then g is continuous. Also, if dou phi by dou t exists and is a continuous function on closed interval ab cross closed interval cd, then G is continuously differentiable and it has the form g dash of t is equal to integral from a to b dou phi by dou t of st s comma t ds. So basically we have to prove if G is satisfying all this hypothesis, we have to prove G is continuous, and also that if dou phi by dou t exists and if it is a continuous function, then we have to prove G is continuously differentiable and it is of the form this. First, we'll prove G is continuous. For that, we are assuming the hypothesis phi from closed interval AB cross closed interval CD to C is continuous and it's defined so. We have to prove that G is a continuous function. Fix epsilon greater than 0, be a positive number. Since phi is continuous and closed interval AB cross CD is compact, phi will be uniformly continuous on closed interval AB cross closed interval CD. Why? Because every continuous function on a compact set will be uniformly continuous. Why this closed interval AB cross closed interval CD is compact? Because it is the product of compact sets. Product of compact sets will be compact. So as phi is uniformly continuous and we have an epsilon greater than 0, there exists a delta greater than 0 such that, so we are going to use the property of uniform continuity such that whenever s comma t s1 comma s2 belongs to closed interval ab and t1 comma t2 belongs to closed interval cd, modulus of s1 minus s2 strictly less than delta and modulus of t1 minus t2 strictly less than delta will imply that modulus of phi of s1 comma t1 minus phi of s2 comma t2 is strictly less than epsilon by b minus a. So consequently, assuming if modulus of t1 minus t2 is strictly less than delta, then modulus of g1 minus g2 is considered, that is equal to modulus of, from the definition of g, integral from a to b phi of st1 ds minus integral from a to b phi of st to ds, that is equal to modulus of, we are taking the integral together, modulus of integral from a to b phi of st1 minus phi of st to ds, and by the property of integral and modulus we can use the inequality here. So less than or equal to integral from a to b modulus of phi of st1 minus phi of st2 ds, right? So that is less than or equal to integral from a to b epsilon by b minus a ds. When this is integrated, you get epsilon by b minus a is a constant, integral from a to b ds, that is equal to b minus a, then you cancel out b minus a and b minus a to get epsilon. So modulus of g1 minus modulus of g of t1 minus g of t2 strictly less than epsilon whenever modulus of t1 minus t2 strictly less than delta will imply g to be continuous. So how did this phi of st1 minus phi of st2 uh, become strictly less than epsilon by b minus c? That you can choose. Yes, you can choose here this epsilon. Instead of this epsilon, we can let it epsilon by b minus a is strictly greater than 0. This b minus a will be always a always a quantity which is not 0. So we can choose so. So what we proved now is that G is continuous. Now we have to prove that G is differentiable with G dash given by this formula. So if we prove that, then from the first part that we just got that if phi is a continuous function, g of t will be continuous, right? So if g dash, if g is uh, differentiable, then obviously g dash will be continuous from the first part, right? As dou phi by dou t uh, is continuous, right? So we just have to verify the formula only. When we prove that g dash of this, that means it is differentiable. Then from the first part we get that g dash will be continuous. Then we are done. Now we are going to fix the point t naught in closed interval CD and assume epsilon is strictly greater than 0. Let phi 2 is equal to dou phi by dou t. Okay. It follows that phi 2 must be uniformly continuous on closed interval AB cross closed interval CD. Why? Because dou phi by dou t exists and is continuous on the set closed interval AB cross closed interval CD, which is a compact set in R2, will imply R2 or C will imply dou phi by dou t is uniformly continuous on closed interval AB cross closed interval CD. That means it follows from the fact that continuous functions on compact set will be uniformly continuous. So you got phi 2, which is dou phi by dou t is uniformly continuous, right? Why do we say that dou phi by dou t is continuous? It is the hypothesis. See, dou phi by dou t exists and is a continuous function. We have it. So since this is continuous, definitely it follows that integral of that will be continuous. So that will give us the continuously differentiable part of that. Okay, so we just have to prove that it is differentiable. What is differentiable? G is differentiable and G dash is this, the formula given. So since this phi 2, which is dou phi by dou t, is uniformly continuous on this set, we are going to use a property of the uniform continuity. If there, that means whenever we already took epsilon greater than 0, that means there will be a delta greater than 0 such that modulus of phi 2 of s dash comma t dash minus phi 2 of s t is strictly less than epsilon whenever the Euclidean distance between st, ordered pair st and ordered pair s dash t dash is strictly less than delta square. That simply means that the point s dash t dash, the ordered pair s dash t dash, uh, is the center of a open unit disk having the radius delta. So the distance is distance between st, the ordered pair st and the ordered pair s dash t dash will be strictly less than delta. right? So what we are going to do in the next step is that we are going to make s remain it as such. That is, instead of v2 of s dash and s, we are going to make s without change here. Okay. And then t and t dash are changed to t and t naught here. Okay. And assuming modulus of t minus t naught is strictly less than delta, obviously, from the earlier inference, we get modulus of phi2 of st minus phi2 of st naught is strictly less than epsilon. Okay, so that is an inference there. So this gives that whenever modulus of t minus t naught is strictly less than delta and a less than or equal to s less than or equal to b, s is definitely varying in between a and b. It is so, we are going to take the value of this term to get to make it into an inequality. That is, we are going to consider modulus of integral from t naught to t phi 2 of s tau minus phi 2 of s t naught d tau. Okay, we are going to integrate it. So the limits are t naught to t. So in order to make it less confusing, we are just rewriting t that instead of t we are going to rewrite it as tau d2. Okay, then that is less than or equal to by the property of integral and modulus, integral from t naught to t modulus of phi 2 of s tau minus phi 2 of s t naught modulus of d2. It will become like this, less than or equal to this term. Okay, and we know that the term sitting here, this one, this will be strictly less than epsilon from the earlier inference. So you can write this is strictly less than epsilon into integrate from t naught to t modulus of d2. That is nothing but modulus of t minus t naught. So we obtain that. Now we are going to fix an S in closed interval AB. Define phi of t, capital Phi of t to be equal to phi of st minus t into phi2 of s comma t naught. Okay. Then we can see that this phi of t, which is equal to the term sitting here, is actually an indefinite integral of phi2 of st minus phi2 of st naught. So in order to make it in memory, this p2 of st minus p2 of st naught is nothing but what is inside this integral or the term here. We were using it before. Okay, just integrate it as an indefinite integral, so with respect to t. Okay, so in this you have take this term, and you know that this phi 2 is nothing but dou phi by dou t, right? We had denoted phi 2 by uh, dou phi by dou t, right? So this is integrating this, you will get what phi of st, that is what you have gotten here. Okay, minus, here you don't have any t. That means this will be acting like a constant when we are integrating with respect to t. So we have a t here. So that's the t here. T into phi 2 of st naught. So this capital Phi of t which we define is actually it is called a primitive or indefinite integral of phi 2 of st minus phi 2 of st naught. Now we are going to use this fact in the coming section. So what does fundamental theorem of calculus say? Fundamental theorem of calculus say if capital F is the antiderivative of capital F dash, then integral from a to b f dash dz is equal to capital F of b minus capital F of a, right? So we know that this capital Phi of t is the indefinite integral of this. So we are going to use that. We are going to again find this modulus of integral. Modulus of, you can see in the left, modulus of integral from t naught to t, phi 2 of s2 minus phi 2 of s t naught d2. That is equal to, so in the fundamental theorem of calculus, you get that the integral is equal to f of p minus f of a. So here you have, instead of f, you have capital P of t. So it's, and instead of p you have t, and instead of a you have t naught. So that means this modulus of integral is equal to modulus of p of st minus t into p2 of st naught minus p of st naught plus t naught into phi p2 of st naught. And then what you do is, you can see here, that is equal to modulus of phi of st minus phi of st naught minus t minus t naught into phi2 of st naught. That will be less than or equal to t modulus of t minus t naught, right? Because we had proved that modulus of integral from t naught to t, P2 of S2 minus P2 of ST naught D2 is less than, strictly less than epsilon into modulus of T minus T naught. So you get, when you solve all these out and use the fundamental theorem of calculus, you are going to get that is less than or equal to epsilon into T, modulus of T minus T naught. That is, this term sitting here is less than or equal to this. And then what you do is divide everything in the left hand side and right hand side of the equality with a modulus of t minus t naught. So it is divided like this. From here, move on like this to here. So modulus of phi of st minus phi of st naught divided by t minus t naught minus the t minus t naught sitting here will vanish. So we have minus phi2 of st naught, which is strictly less than or equal to epsilon. Now you are going to integrate inside and inside the LHS and in LHS and RHS inside the modulus here, and here integrate this. Okay, so you are integrating each term, and that is less than or equal to integral from a to b ds, right? So that will be b minus a. Then what you do is, we know that g of t is equal to integral from a to b phi of st, and this t minus t naught is here, the t minus t naught doesn't have any s here, so it is treated like a constant, right? So you can take it out here, and what remains is 1 by t minus t naught into integral from a to b phi of st minus integral from a to b phi of st naught. So integral from a to b phi of st is nothing but g of t, and integral from a to b phi of st naught is nothing but g of t naught. So you replace that, and the t minus t naught is under in the denominator. Okay, ds minus integral from a to b, the same term, that is less than or equal to g epsilon into b minus a. So this is nothing but g as limit t tends to t naught, g of t minus g of t naught divided by t minus t naught, that happens to be g dash of t naught. So, and definitely this epsilon is arbitrary and strictly greater than 0, so you get these terms are equal, that is limit t tends to t naught, g of t minus g of t naught divided by t minus t naught is equal to the term sitting here, which is what we have to prove, and this phi2 is nothing but dou phi by dou t of st naught ds. So you got that g is differentiable, and from the first part we know, since dou phi by dou t is continuous, integral from a to b dou phi by dou t will be also continuous. That means g dash of t is continuous, and so we can say that it is continuously differentiable. And using this result, we are going to illustrate how to get some answers of integrals. So our claim is integral from 0 to 2 pi e raised to is divided by e raised to is minus z ds is equal to 2 pi if modulus of z is strictly less than 1. Okay. Uh, so we are taking a new function, a modified function of this e raised to is divided by e raised to is minus t into z. There is no t here in the question. We are putting a t here, phi of st. We are making it as phi of st, and we are telling t is varying from 0 to 1 and s is varying from 0 to 2 pi. Okay. Here this phi is continuously differentiable because modulus of z is strictly less than 1. That means it is differentiable everywhere because of the domain we have chosen. Okay. Nowhere the denominator is becoming 0 and so on. Okay. So now, hence, we can say that g of t, which is equal to integral from 0 to 2 pi phi of st ds, is continuously differentiable. That happens to be coming from our theorem. Okay. Also find g of 0. G of 0 will be integral from 0 to 2 pi phi of s0. What is phi of s0? Phi of s0 is nothing but e raised to is divided by e raised to is minus 0 into z. So that will cancel out and you get integral from 0 to 2 pi e raised to is divided by e raised to is into ds. That is nothing but 2 pi. When you integrate, you get 2 pi. Now what we are going to aim is that if we prove, so what we got is g of 0 is equal to 2 pi. We are going to show that g of 1 is equal to 2 pi. Then we can say that g is a constant. That is, that is this term. What we need in the LHS, that is equal to 2 pi. That is what we have to prove. We prove that g of 0 is equal to 2 pi. Okay. So then in the next step, what we are going to do is find g dash of t. So g dash of t is nothing but integral from 0 to 2 pi. The g dash of t is sitting here. And we know what is phi of st. Okay. Uh, so you get, when you integrate, you can understand from this. Phi of st is equal to e raised to is divided by e raised to is minus dz. So dou phi by dou t is equal to, using the uh, quotient rule, you get this z e raised to is divided by e raised to is minus tz. So you differentiated the phi sitting here to get this. So this is g dash of t. Now for t fixed, okay, t is fixed, and take capital P of s to be z I divided by e raised to is minus tz. Take the function. Okay. Then again take the derivative of function with respect to s. Use the quotient rule and you get this. So when you find this, you know that that is nothing but dou phi by dou t. Okay. So in the next step, what you're going to do is, so here we have found out that the phi of s is nothing but the primitive or the indefinite integral of the guy sitting here, capital phi dash of s. Okay, now find g dash of t. G dash of t is equal to this, right? The term sitting here, that is equal to, from the fundamental theorem of calculus. We know that is equal to, so this is nothing but, I can call it p dash of s is equal to, yes, so by the fundamental theorem you get that this g dash of t, which is equal to, this is actually what I can tell you. Okay, I'll write here. So that is equal to integral from 0 to 2 pi capital Phi dash of s ds. Okay, so by fundamental theorem, this is equal to, the guy sitting here is equal to phi of 2 pi minus phi of 0, right? So calculate phi of 2 pi. So phi of 2 pi, when you calculate capital phi of 2 pi, you get it to be Z I divided by 1 minus Ts. Phi of 0 is also equal to Z I divided by 1 minus Tz. So you get phi of 2 pi minus phi of 0 is equal to 0. That means g dash of t must be a constant. So you get what? G of 1 is equal to 2 pi, that is g of t is equal to 2 pi everywhere. So that's how we use the Leibniz rule in advanced calculus to solve that integral from 0 to 2 pi e raised to is divided by e raised to is minus z ds is equal to 2 pi. When you write down the lecture notes, please write this as a question to prove this, and then give the proof by watching out the video. So thank you. And in the next lecture, we'll start with the Cauchy integral formula and the simultaneous sections there, present there. So thank you.